Yeah, let's start. Okay, we have the pleasure to welcome Professor Yijun from Hong Kong Polytech, and he will speak about tick-borne disease modeling, the impact of seasonality, co-feeding transmission, and tick movements among patches. You have about 40 minutes, followed by 5 minutes of discussion, okay?
No, Jacques.
No?
The rule is 30 minutes plus 15-minute questions.
Ah, okay. Bon, sorry. Okay, wait now. 30 minutes. No, okay.
No, it's has been always the same.
A quarter of discussion. Okay, that's good.
Okay. Thanks, Jack, for hosting my talk. And I would also like to thank Professor Pierre Mego for the kind invitation to present our work in this wonderful joint event. So in today's talk, I will present a modeling study to address the impact of seasonality, co-feeding transmission, and tick movements among different patches. So during my talk, if you have any question, you may raise it directly, or you may ask questions after my talk. There are many different tick-borne zoonoses. The most important one is the Lyme disease. It is caused by the bacteria Borrelia burgdorferi, and it is the most common tick-borne disease in the northern hemisphere. In USA, the annual number of cases is around 476,000. In Canada, the annually reported cases are increasing from 2009 to 2016. And the Lyme disease risk is closely related to the tick population dynamics. So the number of endemic areas for ticks is also gradually increasing in Canada with the expanding range of ticks. And the expanding range of ticks is observed in the field experiment. And the main reason are assumed to be the climate change. In Europe, there may be more than 200,000 cases per year. In France, the annual incidence was 53 per 100,000 between 2009 and 2017. The annual incidence of cases consulting in general medical practices in 2019 was 76 cases per 100,000 population. And there are other tick-borne diseases, such as the tick-borne encephalitis, babesiosis, and many others. Here, I will briefly introduce the main feature for the tick-borne diseases. For many tick-borne diseases, the key vector is the exotic tick species, which are most abundant in forests, woodlands, and dense bush. It is totally different from the mosquito species because for ticks, the stages are more complicated, and there are 3 distinct post-egg stages. Normally, we call it larvae, nymph, and adult. Unlike mosquitoes, for larvae, nymph, and adult ticks, they can bite the host, and they may take the blood meals. However, for mosquitoes, only adult mosquitoes may bite host. So this is one of the most important difference between the tick vector and the mosquito vector. For the tick host, the development from one stage to the next is processed by taking a blood meal. Normally, immature ticks should also take a blood meal from their hosts. However, the host species for immature ticks and adult ticks are different. And the immature ticks mainly feed on small animals, such as rodents and other small vertebrates. However, adult ticks prefer larger mammals because adult ticks are more active. And there are two main transmission routes for the pathogen. One is the systemic transmission, and another one is the co-feeding transmission. And if you are very familiar with the mosquito-borne diseases modeling, then you may regard that the systemic transmission route is always considered in mosquito-borne diseases models. And here is the diagram for the systemic transmission route. In the first line, you may see some distinct tick stages: larvae, nymph, and adult. They may bite the host species. And the infected nymph may bite a susceptible host. Then the susceptible host may get infection and become infectious. Then if another susceptible larvae bite this infectious host, then the susceptible larvae may become infectious and develop to infectious nymph. So the main transmission circle is maintained between immature ticks and their hosts. So this is the systemic transmission circle. And from this diagram, you may also say that there are different host species for immature ticks and adult ticks. If an infectious nymph accidentally bites a human, then the human individual may become infectious. So this is the systemic transmission route. However, for the co-feeding transmission route, you may take a look at the diagram A. And when an infectious nymph is biting the same host with a susceptible larvae, then the susceptible larvae may become infectious. So here we have several larvae and the nymphs are biting on the same host individual. And if the nymph is infectious, then the susceptible larvae may become infectious by co-feeding. So the susceptible larvae may molt to co-feeding infectious nymph when they mature to the nymph stage. And in this co-feeding transmission circle, you may say it is not necessary for the host to become infectious. So in this diagram A, the host may not become infectious. However, if you compare the systemic transmission circle in diagram B, if the host become infectious and when a susceptible larvae bites the infectious host, then the larvae may become infected. So diagram B is the diagram for the systemic transmission. Okay, so anyway, we are going to incorporate both transmission routes in the model. Actually, there are many studies on addressing various aspects on tick-borne disease transmission. For example, the stage-structured tick population growth, the impact of the dynamics of tick population, and the host densities on the persistence of tick-borne diseases. The density of different types of host species with different competence of transmission. and the spatial impact or the spatial heterogeneity on the disease risk. Normally, we use a patch model or a reaction diffusion model to describe the spatial dynamics of the tick-borne diseases. The seasonality of tick populations and the disease risk driven by seasonal weather variations. The tick spatial variation and the disease risk when the climate change is considered. The impact of food resources of rodents on tick abundance and the disease risk, and the co-feeding transmission. And if you are interested in more details about different aspects, you may take a look at a brief review by myself and Professor Jianhong Wu, published in Infectious Disease Model in 2017. So anyway, in this work, we are going to present a model by incorporating these three aspects. One is the host movement between different patches. The second one is the two transmission routes, both the systemic and the co-feeding transmission routes. The third one is the seasonal environmental variations. To incorporate the seasonal environmental variations, we are using seasonal parameters. That means the model parameters are periodic with 1 year period. And here are several basic notations in our model. Because we are considering a patch model, so here we have n patches. And a typical patch, for example, the case patch, is described by the notation of the subscript k. So when a variable has subscript k, this means this is the case patch. And for the tick stage, we only use 3 stages: the larva, the nymph, and the adult. We are using L, K to represent the larvae population density in the case patch, NK to represent the nymphs population density in the case patch, and the AK to represent the adult ticks population density in the case patch. And for the ticks and the host population, we divided them into 2 infectious status. One is susceptible class, another one is the infectious class. We don't consider the incubation period. Okay. Therefore, for the host population in case patch, we have susceptible host and infectious host. Here by host, we mainly focus on the immature host. Those hosts are small animals or small vertebrates. We don't consider the host for the adult population or for the adult ticks. For the tick population, we only consider the questing ticks. This means the ticks are finding the host for blood meal. And for the tick host, there are 5 classes: susceptible larvae, susceptible nymph, and the adult nymph. However, for the infectious ticks, we only have 2 stage ticks: infectious nymphs and infectious adult, because we assume all newly emerged larvae are susceptible. Therefore, we don't consider the infectious larvae. That's why for larvae, we only have 1 class that are susceptible larvae. To describe the host movement between different patches, we are using the migration rate from patch J to patch I, MIJ, and we assume the migration rate may also change due to seasonal environmental conditions. So the migration rates are dependent on the time t. Then we can draw this diagram. So here we have larvae and we have nymph. Susceptible nymph, infectious nymph. We have susceptible adult, infectious adult ticks. And for the immature ticks, we consider their host, susceptible host, infectious host. And the susceptible larvae may become susceptible nymph, or susceptible larvae may develop to infected nymph, because during development, they need to take the blood meal. And when they are taking the blood meal, they may get infection due to the systemic transmission or co-feeding transmission. And for larvae, they may develop to susceptible adult or develop to infectious adult. And the development from nymph to adult, susceptible nymph to infectious adult is mainly due to systemic transmission. However, this systemic transmission is between nymph and the adult host, or host for adult ticks. And normally we assume these hosts are deer, large animals, or large mammals. And we don't consider the infection status for deers, because the systemic transmission circle is mainly maintained between immature ticks and their hosts. So we don't consider the infection status for the adult ticks. So this is the diagram for our model. And now we are going to address some details to describe the co-feeding transmission term, because the co-feeding happens when some infectious ticks, suppose these are infectious ticks with red star, and we have some susceptible larvae. When they are biting on the same host, then the larvae may become infectious. And to describe this process, we need some argument. And in our model, we are using the argument based on the binomial distribution. And then we may describe the transmission term. So anyway, here, due to time limit, I'm not going to present all the details. But I need to emphasize that when we are describing the co-feeding transmission term, we need more argument than the systemic transmission term. So anyway, here is the model equations related to the tick classes. So we have susceptible larvae, we have susceptible nymph, infected nymph, susceptible adult, infected adult. Most terms are related to the birth, development, and the death of ticks. However, the terms with blue color represent the systemic transmission terms, and the term with red color represent the, the term with red color represent the systemic transmission term, and the terms with blue color represent the co-feeding transmission terms. And we also have two equations for the host population. And because for the immature ticks, their hosts are divided into two classes, susceptible hosts and infectious hosts. So here we have susceptible hosts, infectious hosts. And again, the hosts may become infectious due to systemic transmission. So here we have a red term. red term to represent the systemic transmission. And we have other terms to represent the movement of hosts between different patches. And we also have the birth term and the death term for the host. And if you take a look at the addition of these two terms, then you may say, actually, we can add these two terms or these two equations together to obtain a single equation for the total host population, because we can cancel this red term and we only have dkh ht minus dkh ht and plus some further terms for the migration. And you say we don't have this birth and the death term, so we only have the migration term for the hosts. So for the host population, we can reduce into k equations to describe the population in, or n equations to describe the population in n patches. And we have the migration matrix MT. And then you may imagine that when MT satisfies some condition, then the host population may remain or may stabilize at a periodic solution. So if the migration matrix MT, because it is a periodic matrix, when this matrix satisfies some conditions, then the host population size always stabilize at a periodic solution. Then we can regard that the total host population density is equal to the stabilized periodic solution. And furthermore, if we are adding susceptible adult ticks and infectious adult ticks together, we can also obtain a decoupled equation. And this equation has the birth term or the development term from nymphs and the death terms, as well as another development term when they are biting deers. So here dk represents the host density for the adult ticks. So anyway, for the adult ticks, we have a single equation in each patch K. So anyway, we may reduce 7 equations for patch K into 5 equations. And the further 3 equations are equations for larvae, nymph, and adult ticks. We have one single equation for infectious ticks, which is the infectious nymphs. And we have one single equation for infectious adult. Now we first study the tick population growth by studying the further 3 equations. And you may easily say that these further 3 equations gives you a monotone dynamical system. And moreover, we only have this kind of nonlinear terms. And by using the monotone dynamical system theory, then we may obtain a threshold result. And the threshold index can be derived as the net reproduction number in patch K. So for each patch, for the case patch, we can define a net reproduction number. And then we can reorder the patch by using the net reproduction number. We assume that the first patch, the patch 1, has the largest net reproduction number, and the last patch, patch N, has the smallest net reproduction number. Then based on the net reproduction number, we can obtain the global dynamics for the tick population growth. So here we have this global stability result. So it says that when the largest net reproduction number is smaller than or equal to 1, then there is no patch in or no tick in all patches. And when the smallest net reproduction number is greater than 1, then there are ticks in all patches. And moreover, the tick population size may stabilize at a periodic solution. And if some patch has net reproduction number greater than 1, but some patch has not have net reproduction number smaller than 1, then tick may remain endemic in some patches, but may go extinction in other patches. So this is the third item. And further on, based on the tick persistence, we can derive the basic reproduction number for the disease transmission. So here are the infected variables for ticks and their hosts. And based on the infectious variables, we can define the basic reproduction number. However, when we are defining the basic reproduction number for the pathogen transmission, we should first guarantee the ticks are remaining endemic in the patch, right? So if the largest tick net reproduction number is smaller than or equal to 1, then you may say that there is no tick in the patch. Definitely, there is no disease transmission in that tick or in that patch, right? So this is the first item. And if the smallest net reproduction number is greater than 1, in this case, we can define the basic reproduction number. And if the maximum net reproduction number is smaller than or equal to 1, then it makes no sense to define the basic reproduction number because there is no tick in each patch. So we cannot define a basic reproduction number. However, if some patch has net reproduction number smaller than or equal to 1, but other patch has net reproduction number greater than 1, then we can still define another basic reproduction number. We use a different notation. Then based on this basic reproduction number, we have the global dynamics for the disease transmission. So here, we have the global dynamics, which is determined by the net reproduction number and the basic reproduction number. However, to define the basic reproduction number, we need to guarantee that ticks can remain endemic in some patches. So anyway, these are the theoretical results for our model. And here, the theoretical results are the global stability results because our model system are monotone systems. And next, I would like to briefly present some numerical simulations. Because our theoretical results are mainly focused on the qualitative results about the disease transmission and the tick persistence. For the numerical simulation, we take some parameters, and some of them are periodic parameters, and some of them are constant coefficients. Then we may say the tick persistence in both patches and the disease persistence in both patches when hosts are allowed to move between two patches, patch 1 and patch 2. However, if two patches are isolated, then the disease cannot persist in patch 2. Here, the blue line represents the disease risk in patch 2. And we can also do some sensitivity analysis. However, from the left panel graph, you may say that the case is really complicated because when you are taking a look at the basic reproduction number and its relationship with the migration rates, then for one migration rate, it is an increasing function. However, for the other migration rate, it is a decreasing function. So the sensitivity relationship is really complicated. And we can do more sensitivity analysis when we are considering a more complicated patch network. So here we have 9 patches, and we use different coefficients for different patches. And then when each patch is isolated, we can derive the basic reproduction number and the net reproduction number for tick population growth. And you may say, when patches are isolated, then some patch has net reproduction number smaller than 1. So this means ticks cannot persist in patch 8, patch 9, and the disease cannot persist in patch 6, patch 7, patch 8, and patch 9. However, when hosts are allowed to move between 9 patches, then here I use different colors to represent the disease risk. You may see originally disease risk is 0 in patch 6, 7, 8, 9. However, when hosts are allowed to move between patches, then the disease may remain endemic in patch 6 and patch 7. We can also obtain more accurate quantitative result about the infected ticks. And here you may say, if we compare 2 different scenarios, when patches are isolated or when patches are connected, then the disease risk may increase or decrease in specific patch. So this gives us the result that the relationship may really complicated. And here are some take-home message. So migration can help or inhibit the tick establishment and the disease persistence. However, the relationship may really complicated. And this talk is mainly based on 2 joint studies. One is myself and Professor Jianhong Wu, published in Infectious Disease Modeling in 2017. And another one is myself and 2 other collaborators, published in Journal of Mathematical Biology in 2021. And thanks for your attention. Okay.
Thank you. Okay, we have 12 minutes for discussion. Comments? Alors, near Poitiers, there is a small company, Valneva, who has developed the first vaccine against borreliose. The vaccine is VLA15, and apparently it works. It's a protein vaccine. They have developed another protein vaccine, classical, against the COVID. And for this reason, Pfizer, 2 weeks ago, has bought Valneva for $300 million. And bon, there is that. Alors, in the susceptible population now, we have a part of vaccinated people and another part of vaccinated, to which I belong, has the weapon, the nuclear weapon against tick, because the tick is dangerous only after 36 until 48 hours after the attack. And it's this period you are taking the tick and taking away the animal, there is no problem. And there is two populations in France. A population of strictly susceptible, a vaccinated population, and population with nuclear weapon. And you know, probably you have in the future to divide the population of hosts, susceptible hosts, in these three kinds of people. You heard me? Because vaccination changes a bit the problem. The vaccination against Borrelia, vaccinated, the tick can peak, but there is no consequence. There is no.
Normally, it's not easy to vaccinate ticks. And there are some studies on vaccinating the tick host species by feeding them some foods.
It's the host who is vaccinated in France. It's the host, it's the human. No, je pense
I think there is a problem of language, Jacques.
Okay.
Of accent.
Vaccine for host.
No, vaccine, not vaccine. Vaccine.
Vaccine, ok. Pour une fois que le I est pareil. Vaccine, ok.
No, I know it's a francophone.
There is a vaccine for host.
I don't think so. To my best knowledge, I don't think so.
No. You have to check on internet. No,
actually, yeah, some companies have developed some vaccines, but some vaccines failed in the third trial. That's why, yeah, there is no mass vaccination programs.
No, it's not mass vaccination program. Yeah. You are perfectly right. But in the future, you have to anticipate and introduce that, perhaps in your equation, for anticipating the mass vaccination.
Normally, when we are modeling the tick-borne disease transmission, or when we are predicting the disease transmission risk, we don't consider the host population in our model.
Okay.
Yeah. This is similar to the case when we are predicting the disease risk of West Nile virus.
And in France,
when we are formulating a West Nile virus disease transmission model, normally we don't consider the human population.
Okay.
We only consider the transmission between the mosquitoes and the birds or their hosts.
But human host is interesting too. Huh?
Yes.
And the protection by the anti-tick weapon is very efficient too. A large fraction of the French population has the extractor. And if you use the extractor just 1 hour after, there is no problem, strictly no problem. In my region, probably half of the population has. I have the weapon in my bag.
Jacques,
oui,
probably you should ask other people if they have any questions. Right?
Oui, mais I
in the room and in
the room. There is many people very interested.
There are several questions in the chat room. So the first one is how to choose the parameters for the host movements. Actually, this is a good question, and I should confess that when we are performing our numerical simulations, we don't check the detailed data for the movements of small rodents. We directly choose these parameters from some literatures.
Yeah, sorry, it's my question. So I was just wondering how this is defined. How do you decide how many animals move from patch 1 to 2 or from 2 to 3? Is that random or like
they have
between
some field
patches?
experiments. They are observing. They catch
right,
the
okay.
animals every year.
Okay, so this is
Yeah.
from field data.
Yes.
Okay. Thank
Actually,
you.
for the Lyme disease, they are a long-term study, in particular, in studying the movement of animals, in particular, the movement of bird migration on the tick and persistence.
Data from
And
where?
every
Sorry?
year they are catching, every year they are catching the birds, migratory birds.
It's data from where? Sorry?
I mean, in Canada.
In Canada. Okay.
Yes.
Thank you.
And
Yeah.
for the small rodents, they also collect the data each year
Okay.
to characterize the movement of small rodents.
Thank you.
Yeah.
Questions, comments, remarks? Alain?
There is another question about the definition of the basic reproduction number. Again, sorry, I skipped some steps. So to define the natural reproduction number and the basic reproduction number, actually, we use the idea from Becker and the idea from Xiaoqiang Zhao and Wendy Wang. Yeah, because there is an ODE or ordinary differential equation system with periodic coefficients. So we can directly use the idea developed by Becker and developed by Xiaoqiang Zhao.
Bacaer. It's Bacaer, not Becker.
Okay, thanks.
Sorry, Nicolas Bacaer.
Yeah, yes.
Yeah.
Okay,
And there is another question. Why don't we consider the adult tick population? And actually, we didn't consider the adult tick population mainly because the adult ticks may have totally different host species, different from the immature ticks. Normally, the adult ticks prefer to take blood meal from deer. From evolution point of view, actually, it's more efficient to take blood meal from large animals than small rodents. Because when ticks are biting small rodents, for example, moths, then the resistance efficient of small mice may be very strong, and that will bring additional death rate for immature ticks. However, when adult ticks are biting large animals, then the resistance or the density dependent death rate for adults may not that large. This is mainly because the host species resistance.
Okay, no question. Thank you very much. We will close the discussion and
Okay, thanks.
Thank you.